Our second class of looking at infinite sets. We'll start by reviewing a little bit of what we talked about last time. So remember, the cardinality of a set is the size of the set, number of elements in the set. And we can use cardinality to study infinity because infinity is a concept, not a number. So we can't just write infinity as a number, but we can make a set that has infinitely many things in it. And we learned that not all infinities are the same size. Sets can either be finite, countably infinite, or uncountably infinite. And an uncountably infinite set has more elements than a countably infinite set, even though they're both infinite. Countably infinite sets can be listed in a procedural order. So that means you can write it down and you can come up with a way to write it down in a specific order. And you can correspond countably infinite sets to the natural numbers. And remember, those natural numbers are 0, 1, 2, 3, and so on. Uncountably infinite sets have more elements than the countably infinite sets. They can't be listed in any particular order. So this includes like the real numbers. Remember, the real numbers are pretty much any normal number that you can think of. Those are uncountably infinite. And the proof that we looked at to show that there are more that an uncountably infinite set has more elements than a countably infinite set was Cantor's diagonal argument. So a little bit of review. Let's go through each of these sets and let me know if the set is finite, countably infinite, or uncountably infinite. So if it's finite, that means it's not infinite. If it's countably infinite, that means you can figure out a specific way to list them in order. And if it's uncountably infinite, that means there's no possible way to list them in a specific order. So let's start with the first one. The set of words in the English dictionary. So all the words in the dictionary, is that finite, countably infinite, or uncountably infinite? Well, Lily, do you want to try again? So remember, infinite would mean it goes on forever. Do the words in the dictionary go on forever? Yeah, this is going to be finite because the dictionary, you can hold it in your hand. You can say these are the words in the dictionary, and there are no more. It has a start and an end, so that's going to be finite. How about the next one? The set of all finite strings of English letters. So if you wrote all possible ways you could write a string of letters in English. Yeah, this one's going to be countably infinite, right? So there's infinitely many possible strings of letters, right? Because you could go as far out as you want. Even if you just had A's, a string of A's, you could have it going as long as you want. So you could have as many A's as you want. So even that would be countably infinite. And we can write them in a specific order because you could put them in alphabetical order, and that would be a way to order them. So that's how we know they're countably infinite. How about the set of negative real numbers? Is that going to be countably or uncountably infinite? I guess I spoiled that it's not finite, but there are, an infinite number of negative real numbers because you could go on as negative as you want. Yep, these are going to be uncountably infinite because remember, if we just take the real numbers alone, those are already uncountable. And then if you just take the negative ones, you didn't really change anything. They're still uncountable. And then the fourth one is the set of non-integer real numbers. So we take the real numbers, then we take away the integers. So that's like 0, 1, 2, 3, and then also -1, -2, -3. Is this set going to be finite, countably infinite, or uncountably infinite? So we start with the real numbers. So that's all possible decimals. So that's like, we could have 0, we could have a half, you could have 1 repeating forever, pi, E, any number that you can think of that's not a complex number. And then you take that set and you get rid of the integers. Are you left with, how many are you left with? You're actually still going to have an uncountably infinite set, right? Because you started with an uncountably infinite set, are real numbers. And the integers are a countably infinite set. So we started with an uncountable set, and we took away a countably infinite set. And so we really didn't take away that many. We just took away the integers, and there's still a ton of numbers left. So it's still going to be uncountably infinite. All right, let's move on. So today we're going to talk about some paradoxes that arise in the context of set theory and infinity. And paradoxes are situations or questions that seem confusing or contradictory or impossible or don't make sense. And they're a good way to explore difficult concepts because they're interesting and they make it easier to understand them. And they often highlight problems that arise in math. So we'll look at a few about set theory and infinity. So this first one is called Hilbert's Hotel. It was discovered or created by David Hilbert in 1924. And this is how it goes. So you have a hotel with infinitely many rooms, and they're numbered. So there's room 1, room 2, room 3, all the way to infinity. And every single room has a guest. So the hotel is full. Then one night, a new guest shows up to the hotel and asks for a room. And the hotel is full, but the person at the front desk of the hotel figures out how to get him a room. How does he do this? How does he do this? If any of you have a guess as to how he does it, I'd love to hear it. 2 of you said the bathroom. It's not the bathroom. A hint is that he can move other people and rooms around, so he can move people to different rooms. So Olivia's on the right track. She says, won't the hotel just add another room since infinity goes on forever? So you're right that since infinity goes on forever, right, we will be able to figure out a way to give them a room. But the question is, where can you get that extra room? Because you can't go to the end of infinity, right? Because it's not going to end and every room is full. So we've got our rooms. Let's say this is 1, this is 2, this is 3, and they're all full. This is 4, and we'll go on forever to infinity, right? And then we've got a new person show up. Not the best stick figure, but it'll do. So what the person at the front desk does is tells every person in the hotel to move to one hotel room with the bigger number, with the next biggest number. So person in room 1 goes to room 2. Person in room 2 goes to room 3. Person in room 3 goes to room 4, and so on forever, right? Every person in the hotel does this. Now we've emptied room 1, and our new guest can empty room 1. Can enter room 1. So that's how with a infinite hotel, even though it's full and we have infinitely many guests, by just telling one person to move over, or every person to move over one room, we can make room for a new guest. And this is Hilbert's Hotel, and this paradox was used to at the start of when all this infinity stuff was being discovered, and it helps you sort of think about infinity, right? Because even though infinity is so big and it goes on forever, we can still interact with it. All right. So I don't think we're going to watch this video right now. I put it in the announcement from last week. I don't know if we have time right now, so we're going to skip it. But here's the next question I'll ask. Is the number of rooms in Hilbert's hotel countably or uncountably infinite? And if anyone has any other observations about how this connects to things we've already learned, that would be great. I want to see one more person make a guess as to whether it's countably or uncountably infinite. Remember, we had an infinite series of rooms and they all had numbers 1, 2, 3, and so on. Yeah, it's going to be countably infinite because we can just think of the rooms as the natural numbers. So 1, 2, 3, and so on. So it's going to be countably infinite. And we sort of talked about how it relates to infinity just now, but Hilbert's hotel, makes infinity a concept that we can interact with and do things to. So it makes it a big concept easier to understand. So this is the next paradox that we're going to talk about. This is called the Banach-Tarski Paradox. In the Banach-Tarski Paradox, you start with a finite set of points that forms a ball. And then we take that ball and we break it into subsets of points and then move those subsets of points back together and form two new balls that are identical to the first one with the same set of points. So what's counterintuitive about this is you start with one ball and without creating any new points, you get two balls. So it seems to violate what we normally think about, because in your everyday life, you can't take a bouncy ball, cut it in half, and then reshape it and get two identical bouncy balls. But in set theory, this kind of thing can happen. So how can we explain this? How can we understand this? To prove the Banach-Tarski paradox, and we're not going to do the proof here. It's a little challenging, but you can look it up on your own if you want. For it to be true, we have to make some assumptions and do some weird manipulation of the points. So the first thing is it relies on this thing called the axiom of choice. And the axiom of choice basically lets us pretend like a countable infinity or an uncountable infinity is countable. So this set of points in the ball up here is uncountable. There's infinitely many of them, but it's uncountable because we can't put them in any specific order. We can't order them, it's uncountable. But we use the axiom of choice in the proof to basically pretend like this is a countable infinity. So the axiom of choice says, let's pretend like there is a way to order them, even though we don't know of one. Know of a way to order them. And then the other thing about this paradox is that you don't interact with it like you interact with Play-Doh or something in the real world. We treat it like a mathematical object that is a collection of infinitely many points. So those are two weird things, two rules that we have when we're doing math that we don't have in the real world that let us take one ball and make it into two. And so the reason the Banach-Tarski is a paradox, right? There's nothing false about it, it's just true. But the reason it's a paradox is because it violates what we normally understand about how we measure things, right? When we're in the real world, we think we have one object, it's just one object, you can't make it into two objects. And so it violates the way we normally think of the world. And this is another example of the way infinity can be weird, right? So you start with one ball, you make it into two. We were only able to do that because there were infinitely many points. All right, this is the last paradox we're going to look at. And this one is not so much about infinity, but about sets. So let's say we have set R, and set R is the set of all sets that do not contain themselves. So take a moment to think about what that means. We have a set, and every single set inside that set does not contain itself. And think about what R is. I have a question for you. Is set R, the set of all sets that don't contain themselves, is set R in itself? Right, so we have set R, it's a circle, or I guess an oval, and every set in here doesn't contain itself. So we have two options. Either R is not contained inside itself. So either R is not an element of itself. And in that case, then R doesn't contain all sets that do not contain themselves. And so that violates what we said in the first place. But if we put R inside of R, we put the set inside itself, then we run into the opposite problem, which is now R contains a set that does contain itself, because now R contains R. So it's a little weird to think about. Let me know if it doesn't make sense, and I'll try to explain it a little more. Another way you can think about it, this is a more concrete example of it, is imagine you have a town with only one barber, and the barber shaves every person in the town who does not shave themselves. Then you have to ask the question, does the barber shave himself? Because if he shaves himself, then he shaves someone who shaves himself, and then he's not shaving only the people who don't shave themselves. But then if he doesn't shave himself, then no one shaves the barber. And then he doesn't shave someone who doesn't shave himself. So it's a thing you have to follow logically, but it's kind of confusing. Well, even if the barber is a kid, then that's someone who doesn't shave themselves, right? And you still get stuck. He's very hairy then. Maybe he's very hairy. Maybe he's a very hairy kid. And that's the solution. So if the barber doesn't shave himself, then the barber becomes someone who doesn't shave themselves. And according to this rule here, that means the barber must shave himself. Right, so then you run into that contradiction. So how do we resolve this, right? How do we come to terms with this weirdness? Basically, the answer is that a set like this can exist. We cannot have a set that contains everything that doesn't contain itself. So far in this class, and by this class I mean the past 6 weeks, we've been talking about something called naive set theory. And naive set theory is sort of where we just say set is any collection of objects. We didn't really define anything super well. I didn't say this is what a set is, this is what I'm allowed to do with it, this is what I'm not allowed to do with it. And so when Russell came up with this paradox, mathematicians said this is a problem. We need to start over with set theory and define it better and come up with better rules so that we don't have paradoxes like this. And the guys that invented, or I guess discovered, this new set theory were named Zermelo and Frankel. So this is called Zermelo-Frankel set theory, or ZFC. Yeah, so this is sort of how we get around Russell's paradox. We're not going to get into the details of ZFC here because it's kind of challenging, but it is interesting, and you're welcome to read about it on your own. So now we got through all that first stuff pretty fast. We might return to some of the videos we had at the end if we have time. But real quick, I want to go through everything we learned so far in the class because we learned a lot of variety of things. And hopefully you guys can remember as much of it as possible. I do not have a Kahoot today. I felt like the things we were talking about are not super compatible with Kahoot. So unfortunately I do not have one. So this is what we learned in the first class. We talked about that a set is any collection of objects, and that's the definition that we've been working off so far. And we have a lot of notation that we use for sets. We learned that this epsilon means is an element of, this sideways U means is a subset of, this U means union, and then upside down U means intersection. And then subset means a set that's contained inside another set. Union means the set of all elements that's in either of two sets. And then intersection is the set of all elements that's in both sets. We talked about some sets that we use commonly. The 0 with a slash through it is the empty set or the null set, the set that has no elements. N is the natural numbers, so this is like 1, 2, 3, 4, and so on. Then we also have the whole numbers, that's like the natural numbers, but also with a 0. And then we have Z is the integers, that's like the natural numbers or the whole numbers, but also including negative numbers. And then we have Q, that's the rational numbers. We didn't talk about those guys as much. And then we have R, those are the real numbers. We learned about some relationships between sets. We have set difference, A minus B is a set of all elements that are in A but not in B. We learned about the symmetric difference, which is the set of elements that's in A or B once, but not in both sets. We learned about cardinality, that is the number of elements in a set. And then we learned about set builder notation. This is a way we can build sets, that we can talk about sets. So for example, this one, set A is a set of all x in the natural numbers such that x is less than 5. We talked about power sets in Cartesian products. P of A, or 2 to the power of set A, you would really just say the power set of A. This is the set of all subsets of A, so every set that's inside A. The Cartesian product, A times B, or A Cartesian product B. This is the set of all ordered pairs, A and B, where A is an A and B is an B. So basically, every way you can order two elements, one from A and one from B. And we learned that we can use the Cartesian product to construct the coordinate plane, right? So we have this guy that you use a lot in math, like algebra, but we can construct it using set theory. So this is really just a set of points. That is the Cartesian product of the real numbers times the real numbers. Then we talked about some way you can use set theory and probability. Probability is the likelihood of an event happening, and we define it as the number of successes divided by the number of total outcomes. And we can use set theory to consider the, I guess this should say probability of outcomes. We can use set theory to look at the probability of outcomes. And so we had one set, that was the sample space, and that was a set of possible outcomes for something to happen, the way something had happened. And then we can define probability as the cardinality of the set of successes divided by the cardinality of the set of the sample space. Okay, that was pretty fast. We've got some time, so we can do those videos. If you have any questions, anything I went over too fast, please let me know. We will do these videos, so I'll stop sharing and set them up.